Okay, welcome to another tutorial. This one, it's actually going to be a change of pace. It's going to be in XNA. And what we're going to cover, as you can see from the title, is creating an FPS camera, a first-person shooter camera, complete with keyboard movement and mouse movement. A lot of the times you'll see camera tutorials for XNA, and they just show you how to set up the view and projection matrices, and they don't really go into or the keyboard input, but they don't go into mouse movement. So we're going to cover that, and it's going to be a long tutorial, which, let me just say that, as you can probably see from the YouTube. But we're because in order, after we make the camera, we have to actually render something to show that the camera is actually working. So what we're going to do is, in addition to just creating the camera, we're going to create a simple floor class, which will allow us to render basically a tiled floor, so that we can, theoretically walk around on. So to start, we're just going to create a new project, Windows game, call it camera tutorial. When it opens up, I'm going to run it just to see if it works. Okay, there we go. Now we're going to create a class, just call it camera, and we're going to import XNA, and for later we're going to need input, so we're going to import that as well. And this camera class is actually going to be a game component. Now, if you don't know, game components in XNA essentially get added as a component to the game's components list, and then it gets hooked up to the game's update, draw, initialize methods, so that you never have to actually call the camera's update, etc. if you just override the the inherited update method. It also comes with some good stuff like a graphics device, etc. So to start, I'm going to create some attributes. Now, the first one is going to be a vector 3 called camera position, which is going to hold our camera's position. Next one is going to be a vector 3 called camera rotation, which is going to hold all of our rotation values. Next one's going to be a float camera speed, and we're also going to need a vector 3 called camera look at. Now, the look at vector essentially defines the direction. It's the vector in the direction which your camera is currently looking. Now, that also includes whether or not your camera's rotated. So if you're looking up with the camera, it's the vector pointing in the direction up slightly at an angle. So you have to take into account when building your camera look at the target vector, what your camera's orientation is. So we'll go over that. Properties. We're going to have a couple properties. The first two that we're going to create now are the projection matrix property, which is going to have a get and a protected set, which we're not actually going to define. We're going to have it auto create these for us. The next one is the matrix called view, and it's just going to have a get, and it's going to return matrix.create look at. It's going to take in camera position, our camera look at, and vector 3 dot up. Now, the view matrix defines exactly that, what I was saying before, but essentially just the entire view of the camera. So that includes where the camera's located its current target vector and the up vector. So it's essentially creating a transform with forward, up, and the relative camera position, and it's defining all that. So and the view and projection are needed for rendering objects based on the camera's orientation in the 3D space. So we're also going to need a constructor. Whoa. It's going to take in a game. We're first just going to set up, this is how you set up the, because it inherits from game component, it needs to initialize using the base constructor, which just takes in a game. Now what we're also going to pass in is a vector3 position, vector3 rotation, and a float speed. Now, before we what we're going to do is actually create a before we set the position and rotation, we're going to create a method that essentially just moves the camera to that position with that rotation. So it's just going to set the so camera rotation equals rotation, and what we're going to do is set camera speed equal to speed, set up our projection matrix. So projection equals matrix dot create perspective, because we're using a perspective. There's two types of projection matrices, by the way. There's orthographic, which is basically completely two-dimensional, where everything is essentially the same size relative to what the camera sees. So you live in a perspective. You have yourself a perspective view. Your eyes have a perspective view. So that's what we're trying to build with a first-person camera. We're trying to build a more realistic view. So you have to use a perspective view, which takes into account an angle, field of vision, or field of view. So to start, for the field of view, we're going to use mathhelper.pi over 4, which is essentially just 45 degrees. Now for the aspect ratio, we're going to use our game property, graphics device, viewport, aspect ratio. For the near plane, we're going to put something very small like 0.05 and something large like 1,000. Because you'll never notice things popping into existence 1,000 units ahead. If you put it somewhere closer, like 50 units ahead, you'll see things randomly appear because the draw distance. It's otherwise known as the draw distance. You'll hear that in games like Skyrim. Skyrim on PC has a larger draw distance. You can see things farther away. And finally, we're gonna set the camera position and rotation. So we're going to move the camera to position, rotation. There we go. Now, what we want to do first, before anything, is set up a method that will help us create our correct look at our correct target vector. Because remember what I was saying is if we move the camera at all, rotate it at all, our target vector breaks down. It's no longer the correct target vector. It would be the correct target vector if we had no rotation at all and we were just a character that looks straight forward the entire time and just strafes around. But that's not a very good game, and that's not a first-person shooter camera, so we're going to have a method called update lookat, and all it's going to do is first build a rotation matrix from our rotation, camera rotation .x times matrix.create rotation, camera rotation .y. So essentially what we're doing is we're just taking both a matrix containing our camera rotation from the x, our camera rotation from the y, and yaw and pitch, and we're adding those to a new rotation matrix. Now, using this rotation matrix, what we're going to do is create a lookat offset vector, which essentially will just be the change in our lookat based on our rotation and the base reference, which was our forward vector, our unit z. So vector3 look at offset is equal to vector3 dot transform. So see how vector3 transform takes both a position, which will be our vector3 dot unit z, and our rotation matrix, and it'll build that offset. Now, using that offset, what we can do is essentially just update our cameras by adding our camera position plus lookat offset. So there we go. So our camera lookat is correct. And anytime our camera position changes or our lookat offset changes based on our rotation matrix, we need to update that. So if you think about that, then there's a problem with the way we set this up. I mean, I purposely did this just for the tutorial, but this what we need to do is anytime these change, we need to update the lookat. So the easiest way to do it would be to create a couple properties for our position, which will just return camera position. But in the set, what it'll do is camera position equals value, but then right after that we're going to call update lookat. We're going to do the same thing with our rotation. It's just going to return camera rotation, but right after we set this, we want to call update lookat. So then, now that we have these two properties set up, if we just change this to position and rotation, it's fine now. So anytime we change the position or rotation, it will call update lookat and do all the work for us. So now we're going to want to create the update method. So override void update. And in here for now, just create a delta time variable, which is equal to float game time dot elapsed game time total seconds. And this will be used to have smooth animations, so smooth mouse movement, smooth, which some people don't like, by the way. I know some people, extreme FPS computer guys don't like a lot of the time smooth mouse input. But for this tutorial, I mean, you can just remove the smoothness. But yeah. So the next thing we want to do is create our well, actually, for now, what we're going to do is just see if all of this worked, because this should, without movement, be able to create a scene for us. Granted, we have something to actually draw. So the next thing we're going to do is the second part of the tutorial. We're going to create the floor class. So create a new class called floor, and we're going to need to import Microsoft XNA Framework and the framework.graphics. So the floor class is going to have a few attributes. Now it's going to have a private int floor width, private int floor height. Now floor height meaning essentially floor length in the z direction. So don't confuse it with floor height as in the y direction. It's going to need a vertex buffer, floor buffer. It's going to need a graphics device and a color array which we're going to use to alternate colors of the different tiles. So we're just going to have it be color.white and color.black. So it's going to end up being like a checkered floor. So in our constructor, what we're going to have is we're going to have it take in a graphics device, a width, a height, and just set up these attributes. Now, there's only essentially two methods we're going to have in here, besides the draw, of course. So 3 methods. One is going to be, we're going to build our vertex buffer. So private void build floor buffer. And essentially in here, what we're going to have to do is create a list of vertex position colors, which are going to be our vertices of that we're going to use to draw. We're going to add those to our vertex buffer, because that's essentially what a vertex buffer is. Vertex buffer just defines a list of vertices that are going to be used by the graphics device to be drawn to the screen to render geometric primitives in 3D. Now, the next thing we're going to want is a counter variable. Now, we can just set this to 0 for now, and then we want to, now first I should explain what the counter is for. The counter is going to be used, we're going to increment that when we loop through to basically generate the tiled map, and we're going to do a modulus operator on the counter, so that we can alternate the colors of the tiles. Because anything modded, since we only have 2 colors, if you mod the counter by 2, anything modded by 2 either returns 0 or 1, true or false. so we'll be able to swap on and off. So what we're going to do is loop through to create. So it's going to be a nested for loop. That's just going to be go through based on the size of the map. Now here we're going to want to increment the counter once for this run through. Height Z++. I use Z here instead of Y because, again, conceptually for height we're talking about the Z into the screen, not Y upwards. Now again, we're going to want to increment the counter. Now here we're going to have a for each loop. Now before we can even do the for each loop, we have to have something to loop through. Now currently what we need to loop through is essentially a list of vertices so that we can add them to the vertex list that we're going to then use to create our vertex buffer. So to do that, we're first going to have a method that tile in our floor. So essentially this will just return it will return a list of these vertices to us. So to start, we got to create a new list of vertex position colors, and we're just going to start adding new vector 3. Now what we're going to have to do is use these X offsets and Z offsets to adjust the where we're drawing these in our 3D space. Because we didn't have the X offsets or Z offsets, they'd just all be on top of each other and it wouldn't actually create a grid. So 0 plus X offset would be the first vertex to create of the first triangle. Now since these are rectangles, squares, in order to create a rectangle you need 2 triangles. Now triangles are made up of 3 vertices, so in total we're going to have 6 vertices. So this is going to be the first vertex. 0, the Y is always going to be 0 since we're not going in the Y direction. It's just going to be at level 0. And 0 plus Z offset for this, and tile color. Now for the next one, we're going to want 0 plus X offset, I believe. 0 again, and then 1 plus Z offset, I think will work, if I think about it correctly. Okay, I was just checking something. Wait. You know what? I forgot something. These have to be vertex position colors. And just throw all of that. And I'm going to do some copy pasta. Paste that down there. Essentially, I'm just going to copy and paste for a lot of these. Actually, yeah, do this, copy and paste it instead of just typing them out. Copy and paste that code 6 times because, as I said before, we're going to need 6 of these anyway. And if we think about this, the first one, yes, should be 0, 0, 0. What I said before, 0, 0, 1, I don't think was necessarily correct. because if we're at 1 all the way to the left per se, or if we're at 0 or at the middle, then we want to go all the way to the left. We then want to go all the way back to the right. And then we're going to have to go back to this vertex because it has to be in clockwise. If you don't do it clockwise in the same direction, then it won't render correctly. For this one, it would be 1 in each, in the X and 1 in the Z. And then for this, it would be back to 1 there. And that should be correct. And just return that. And that should be fine. Now up here is where we're going to create a loop. We're going to create a for each. In floor tile, we'll pass an X, pass an Y, and pass Z. I'm confused myself now. Floor colors, and here's where, remember, counter modulus 2. Vertex list dot add vertex. Now outside of this loop, that'll add all the vertices that we need in that list. So we'll have this massive map. And now we need to create our buffer. So floor buffer equals new vertex buffer, and this takes in device, vertex position color dot vertex declaration will be the type. The vertex count would be just vertex list dot count, and buffer usage would just be none. Just put it to none. Now the last thing we have to do is just set data, and we have to designate the type, vertex position color, and then it takes an array, so vertex list dot to array. So now our buffer is created, so the only method that we still need is the draw method. Now this is going to be public void, and it's going to take in a camera. And oh yeah, and a basic effect. A basic effect essentially is code. It's basically HLSL, high level shader language code, wrapped up in a C# class, so that you don't have to ever like deal with writing your own shader code. So in here, that effect, we are going to have to do some stuff to. Vertex color enabled, we're going to set to true. We're going to set the view equal to camera dot view, the effect dot projection equal to camera dot projection, and effect dot effect dot world equal to matrix dot identity. And now we're just gonna loop through and draw each vertex. Draw each tile. So for each effect pass in effect.currentTechnique.passes. What we need to do is call pass.apply, and then we need to set the buffer, set vertex buffer to floor buffer, and then we just want to draw primitives. Primitive type triangle list 0, and then for buffer dot vertex count divided by 3, because there's 3 vertices per triangle. So if you divide the total number of vertices or vertexes by 3, that's the number of triangles that you're essentially going to draw. And I think we're done with this class. Now, what we can do now is we have our camera. It doesn't move around yet, but what we can do is we can create the camera. We can create a floor. And in initialize, what we'll do is create a new camera. Oh, for some reason it's not working. Oh. Wow, that was a really dumb error. I'm tired, but excuse that error. I just got confused for a second. New vector 3, and set it to something. Set it to 10, because we want to be sort of oriented near the center of the map, and since we'll make it like 20 by 20, that'll be good. 1 for Y, move it up, and 5 in for Z. I'm just gonna make these all floats. Rotation, just give it 0. If it wants to not freeze on me, and then 5 for camera speed. Doesn't matter right now, but we're gonna create a new floor. We're going to pass in graphics device. We're going to 2020. One other thing that I forgot is that we're going to end up needing a basic effect, because floor's draw method uses one. So effect equals new basic effect. Pass in graphics device. And if you move down to the drawing, all we have to do, or all we should have to do, is call camera and then effect. And there's one more thing that we did forget, is because camera's a game component, we can add it to the components of the game. So if we run this right now, we should get, hopefully, not that. Now it says floor buffer equals null. That's because we forgot a crucial step. We should probably build the floor buffer. Completely forgot. So yeah, we need to actually call our build floor buffer method in the constructor. And there we go. So you have a camera and a floor. And as you can see, it's kind of like a chess or checkers grid being drawn. So now the next step is we're going to actually have the camera move around. And we're almost there. We're almost there. So if we look at this, we have updating, look at, we have a move to. What we don't have is an actual move method. So there's two things we could do. We could just we could create a method that will allow us to do later on, or allow you, because I'm not sure if I'm going to do a complete 3D XNA game series. I'm thinking about it, but it would be good to have a method that would essentially simulate moving but not actually changing the camera's position, so that you can use that the vector return from that to check it against collision bounds. So if you want to implement your own simple collision without like a physics API like Havoc, you can go and just check it against bounding spheres or boxes and check to see if that vector 3 isn't contained within it, and then you can have your camera move. If it is, then you stop all movement. So we're going to create a method that so essentially private vector 3 preview move vector 3 amount. So this amount is going to be the amount that you're moving by, so that basically the scale factor. And now what we're going to do is create a rotate matrix. Again, another rotation matrix, but this one has to do with the actual movement. This one is only going to include the Y, the rotation around the Y-axis when you sort of move the mouse, so the turning motion. So matrix rotate is equal to matrix dot create rotation Y, camera rotation dot Y. And now what we want to do is we want to create essentially a movement vector containing the values from amount, and then we're just gonna set that equal to the transform of itself and our rotate. So we're just going to get that vector transformed by that rotation matrix, and then we're just going to return our camera position plus the movement vector. So this will return basically the value of our camera position incremented by that movement, so without actually changing the camera's position. So then we want to create one more method that will actually move the camera. So by a scale factor, and then we're just going to call move to and then pass in preview move with scale and give it our rotation, because we're not changing the rotation. We're just going to pass in our rotation to set rotation to itself, but we're going to set our position equal to the value returned by preview move. So let's see this in action. Now, first we're going to need a keyboard state. And then we're also going to need a vector3 move vector, which will just basically hold the direction in which we're going to move, up, down, left, or right. So move vector dot z equals 1 if ks keyboard state is key down keys dot s. Move vector dot z equals negative 1 if ks dot is key down keys dot a. Move vector dot x equals 1, and then if ks dot is key down keys dot d. Move vector dot x equals negative 1. So now that we have our move vector determining which direction we're actually moving, if move vector doesn't equal vector 3.0, so if we are actually moving somewhere, what we want to do is normalize that vector so that we don't move faster diagonally, because what happens is, because of Pythagorean theorem, what happens, and other reasons too, when you are moving diagonally, you end up moving faster, like how, the hypotenuse of a triangle, length is always greater than the two, has to be greater in order for it to be, like a right triangle. It has to be greater than the other two sides. So that's what ends up happening. Now, if you normalize that vector, it turns into a unit vector. So no matter where we move, we'll always be moving at the same speed. So first, we're going to move vector dot normalize, and now we add in the smooth factor and our speed. So delta time times camera speed, and now move camera. So we're just going to move by move vector. So you want to see if this works? Let's try it out. And there we go. We're moving around. And we're moving the same speed, diagonally, forward, backward, left, right. It's all working well. Now, the next part is a little bit more complicated, which has to do with mouse, handling the mouse. But then that's it. So what we're going to do is close this and create 2 more attributes. 3 more, actually. One of them is going to be a vector 3 called mouse rotation buffer. The next one is, of course, going to be a mouse state, current mouse state. The other one is going to be a mouse state, previous mouse state. Now, the we need to, the reason I have a previous mouse state and a current mouse state is we need to keep track of, for various reasons, the changes in mouse states. So we need to set up previous mouse state equal to mouse.getState in the constructor, and then in the beginning of our update method, set current mouse state equal to mouse.getState. Then down here at the end, set previous mouse state equal to current mouse state. So now comes the fun part. We have to figure out a way to do the mouse movement. Now, the first two things we need are to keep track of the change in mouse movement across the viewport. So to do that, we're going to create two float variables that are just going to hold the mouse position. And then if current mouse state doesn't equal previous mouse state, we're going to handle all of our mouse movement code. So in here is where we're first going to cache the mouse location. So delta x is going to be equal to current mouse state dot x minus game dot graphics device dot viewport dot width divided by 2, and then delta y is going to be equal to current mouse state dot y minus game dot graphics device dot viewport dot height divided by 2. Because we only want to change between the because what I'm gonna do is we're gonna always have the mouse be set, its position set in the very dead center of the viewport. We only want the delta x and delta y to be relative to halfway down the viewport and halfway across the viewport, and that change in between those from the top to the bottom. So that's why we have to subtract the width of the viewport divided by 2 for each of these in the height. Okay. Yeah, okay, that was preview move. Okay. So now what we want to do is remember the cached mouse rotation, mouse buffer. What we're going to do is we're going to add to that basically or subtract from that, from the x, 0.01 f times delta x times delta time minus equals 0.01 f times delta y times delta time. And what this will do is it'll add that smooth mouse movement essentially, and this will basically create our rotation. Now that we have a rotation, at least on our buffer being created, eventually we're going to actually need to set our rotation to something. But before we do that, we need to clamp the rotation, because we don't want the camera to be able to rotate over itself, like just completely like do barrel rolls, like do a barrel roll. We don't want to have the camera do that. So we have to pick a degree range to essentially clamp the rotation between. Now the best range I've thought is 150 degrees, so negative 75 to positive 75. So instead of allowing them to have 90-degree view up and down, straight up and straight down, you kind of limit them by like 15 degrees or so. So to do this, if mouse rotation buffer dot y is ever less than math helper dot 2 radians negative 75.0f, we need to set the rotation buffer dot y equal to this minus itself minus math helper dot 2 radians negative 75.0f. Now essentially what this does is it's similar to if you've ever had to deal with using 2D images and them colliding with the bounds of the viewport. It's essentially the same concept in that what we want to do is if you ever are less than math helper dot 2 radians, so if you're ever below that, we want to clamp it, do our own sort of clamp, and not allow you to go beyond that. So then if mouse rotation buffer dot y is ever greater than math helper dot 2 radians positive 75, we want to do the same thing just with the positive. So there we go. So now the only thing left to do is essentially set up the rotation. So to do that, we just need to set a new vector 3, and now in here we're going to have 3 values. The z value is going to be 0 still because we're not doing any rolls. So we're not rotating around the z-axis, but the 2 axes we are rotating around are the x and the y. So what we want to do is negative math helper dot clamp, and this takes a value which will be mouse rotation buffer dot y and what to clamp it from. So math helper dot 2 radians pass in negative 75.0f, and for the max pass in positive 75.0f. So there you go. So you're clamping it. Now why it's negative I'll show you in a second when we actually go and run. But the next thing is math helper dot wrap angle. Now we want to wrap the rotation buffer. We want to wrap the rotation buffer, the x value of the rotation buffer, because what wrap angle does is it reduces the given angle to a value between pi and negative pi. So essentially it'll just clamp it to 360 degrees. That's essentially all it'll do. So that we're never getting beyond that, because if you do, the buffer will continue to, because up here, since we're just continuously subtracting from it, after a while, after time, you'll end up rotating extremely fast. So if you didn't wrap the angle, then you'll have some serious problems. So apparently there was a problem with clamp. Float max. Oh, okay, there we go. And there was one extra there we go. And now underneath rotation, I believe delta x needs to be set to 0 and delta y needs to be set back to 0. We need to reset them after every run through. And down here, we should set the position to game.graphicsdevice.viewport.width divided by 2 and game.graphicsdevice.viewport.height divided by 2. And because we want the cursor to be in the dead center of the viewport and stay there, so let's run this. And as you can see, we have perfect. We're rotating correctly. We can look up, we can look down, we can look over, we can go all around. Now, as you can see, the mouse is kind of freaking out because there's problems with setting the mouse cursor position in the center. It'll still show up in weird instances, but generally you have all the functionality. You can look up. It's smooth. There you go. Now, oh, by the way, if you do set the position, the only way to close it now will be to hit Alt F4. Now, what I did want to show you is you might wonder why, why is this negative? Well, let's say we remove the negative. Now, you've just inverted the mouse position. So, I mean, if you think about it, if you want to have an option to invert mouse position, all you'll have to do is just change this from negative to positive and back to negative. So there you go. That is the simple FPS camera class. It works pretty well. If you have any questions, just leave comment. I will have a link to the source code, the complete source code for this project, just for the classes, not the entire project itself, up on at a link in the description of the video. So I hope you enjoyed the tutorial. Thanks for watching.